Okay, welcome to the deep dive. Today, we're plunging into a seriously fascinating area, the profound impact of artificial intelligence, AI, on chemistry.
Yeah, it's huge.
And this isn't just, a small tweak. We're talking about a fundamental reshaping of how chemical research even happens.
That's right. And you've given us this great set of sources, notes, guides, timelines, really mapping out this whole revolution.
So our mission today is to unpack all of that for you.
Yeah, get into the core concepts, figure out what's driving it, look at some landmark achievement.
Where AI really made a difference.
Exactly. And the tools chemists are using now, how molecules get sort of translated for AI.
And how the chemist's job itself is changing, which is maybe the most interesting part.
Could be.
Think of this deep dive as, well, your shortcut, your way to get genuinely informed about what's happening in this incredibly fast-moving field.
Because the big shift, like you said, is AI moving chemistry away from just intuition and, let's face it, often painstaking trial and error,
Right.
towards being really powerfully boosted by computational smarts.
It's opening up avenues that were just, well, too complicated before, too vast.
So we'll cover the basics from the sources, AI versus ML versus DL, what's the difference?
Mhm.
And that perfect storm idea,
Mhm.
the factors coming together.
Plus those big examples, AlphaFold,
Yeah.
Halicin.
Yeah, the big wins. And then the different ways ML is used, the supervised, unsupervised stuff.
How you actually represent a molecule for the computer.
Crucial step. And then, yeah, that future partnership, humans and AI.
Okay, let's dive in. You hear AI, MLDL thrown around constantly. The sources start by defining them. Let's clarify that hierarchy. AI first, the big one.
Right. So AI, artificial intelligence. The sources frame it as the broadest concept. It's really about building systems that can do tasks we normally think require human intelligence.
Like pattern recognition, reasoning, learning.
Exactly. All those things. It's the big umbrella term, the overall goal.
Got it. AI is the big dream, mimicking intelligence. So where does machine learning, ML, fit? That seems to be where the action is, practically speaking.
Well, ML is a major part of AI, a subset. And the key idea is that the algorithms learn patterns directly from data.
Without someone programming every single rule.
Precisely. They adapt, they improve, just based on the data they process. They learn from experience, essentially.
So rather than me writing code that says, if molecule has this feature, predict this property, I just give the ML algorithm loads of examples of molecules and their properties, and it works out the connections itself.
That's the core idea. It learns the mapping, and then within ML, you've got deep learning.
Ah, okay. The famous one.
Yeah.
Neural networks and all that.
Yeah, deep learning, DL. It's a specific type of ML. It uses these complex structures, artificial neural networks, with many, many layers.
Inspired by the brain, sort of?
Loosely, yes. The deep part just means lots of layers. And what makes them so powerful is they can automatically find really intricate hidden features in huge, messy data sets.
Without needing a human to point them out first.
Often, yes. It reduces that manual feature engineering step. So if standard ML might need you to pre-process the data and tell it what features are important.
But like maybe the number of rings or specific functional groups.
Right. Deep learning, particularly with something like a molecular graph, might just figure out the important structural patterns directly from the raw structure through its layers.
Wow, okay, so it learns the important bits on its own.
That's the goal. They're really good at finding complex patterns in things like images, text, or, complex chemical data.
So understanding that stack AI is the goal, ML learns from data, DL is a powerful type of ML using these deep networks that helps chemists navigate the options.
Definitely. Helps you pick the right approach for your problem.
Okay, clear enough.
Yeah.
Now, why is this AI and chemistry thing happening now? The Swabies keep calling it a perfect storm. What are the pillars holding this up?
It really is a convergence. Pillar number one, maybe the most obvious, is just the sheer amount of data, the data deluge.
Right, we're just generating way more chemical information than ever before.
Exactly. Unprecedented amounts. From high-throughput screening, HTS, the robots testing thousands, millions of compounds super fast.
Yeah.
And combinatorial chemistry, making huge libraries of similar molecules.
And those big public databases the sources mentioned, PubChem, JML.
Absolutely vital. PubChem is this enormous repository gathering data from everywhere. And crucially, it includes negative data, things that didn't work.
Which is just as important for training, isn't it?
Absolutely. You need to know what fails too. CHAM is a bit different, more curated. It focuses on bioactive molecules, drug-like properties,
Hmm.
really high-quality structured data.
And for proteins, the PDB.
The protein data bank,
Drug-
essential. The primary source of the 3D structures that, well, AlphaFold 2 learned from.
So data from labs, robots, curated databases.
Oh,
What else? Computational data, too, like
Yeah.
DFT.
yeah. Computational chemistry itself generates massive data sets now. Things like density functional theory calculations can simulate properties for vast numbers of molecules. Datasets like OML25 were made exactly that way, specifically to train AI.
So wet labs, robots, databases, and simulations, it really is a flood.
It is. That's pillar one.
Okay, pillar one, data everywhere. Pillar two.
Algorithmic advances, especially in ML and DL. I mean, decades of computer science research have yielded incredibly powerful algorithms.
The deep neural networks we just talked about.
Exactly. They're now sophisticated enough to actually find the meaningful signals in that data flood. And new architectures like convolutional neural networks, CNNs.
Were images originally?
Yeah, but adapted.
Yeah.
Recurrent neural networks, RNNs, for sequences like smile strings, and especially graph neural networks, GNNs.
For the actual molecule structure.
Right. These newer methods can tackle chemistry problems in ways older algorithms just couldn't. They need less hand-holding.
They find the important features themselves. Okay, so loads of data, smart algorithms. What's the missing piece, the final ingredient?
You need the muscle to run it all. Computational power.
Ah,
Running these complex algorithms on these huge data sets takes, well, serious horsepower. And the game changer here has been graphics processing units, GPUs.
the chips from video games? Seriously.
Seriously, GPUs are built differently than standard CPUs. They have thousands of tiny cores designed to do lots of calculations all at once in parallel.
Like an army of calculators instead of one big one.
Kinda, yeah. And that parallel structure, it turns out to be perfect for the math involved in training deep neural networks, matrix multiplications mostly.
So what used to take ages on a normal computer?
Exactly. Training runs that might have taken months can now be done in hours or days using GPUs. It just massively speeds up the whole research cycle, lets you try more complex things.
Okay, that makes total sense. You need the data, the smart algorithms, and the power to run them at scale. They really feed off each other, don't they?
Totally synergistic. More data improves algorithms, better algorithms can handle more data, faster computers enable both. It's this positive feedback loop driving everything forward.
So with this perfect storm in place, where's the proof? Where has AI actually, delivered something amazing? The sources pick out a couple of landmarks.
Yeah, two really stand out. First, DeepMind's AlphaFold 2, predicting protein structures.
That was massive news, right? Figuring out how proteins fold into their 3D shapes, that was a huge problem for, 50 years?
A grand challenge, absolutely. Knowing that 3D structure is key to everything, function, interactions, drug design.
And AlphaFold 2 just solved it.
Well, it achieved incredible accuracy. Trained on the PDB data, it could predict structures often as accurately as experimental methods like X-ray crystallography.
Which is amazing. What's the impact?
Revolutionary. For structural biology, drug discovery. It gives researchers reliable 3D models of proteins, even ones hard to crystallize. You can use these models for virtual screening, testing millions of potential drug molecules computationally.
Speeds things up enormously.
And accelerates basic science too. Plus, they made the AlphaFold database, the AFDB, putting millions of predicted structures out there for free. Huge for democratizing research.
Okay, that's genuinely transformative. Making the difficult computable. What's the other big one from the sources?
The discovery of Halicin, a new antibiotic.
Also a huge deal, right? Finding new antibiotics, especially with resistance growing.
Critical global need. And this came from researchers at MIT, James Collins, Regina Barzilay. They used deep learning.
Ow!
They trained a model on molecules known to inhibit E. coli growth. Then they unleashed this model on huge digital libraries looking for molecules with predicted antibacterial activity.
So it wasn't just finding known antibiotics, but spotting the features that make any molecule antibacterial?
Exactly, a functional prediction. And it flagged Halicin, which was fascinating because Halicin had been looked at before, for diabetes, I think, but nobody realized it could kill bacteria.
AI saw something humans missed.
Completely overlooked, and Halicin turned out to be special. Unique structure, totally new mechanism. It messes with the bacteria's energy production.
Wow.
Broad spectrum, worked against tough bugs, and crucially, Bacteria seem slow to develop resistance to it in lab tests.
Incredible. And they named it after HAL 9000.
They did.
Right.
Perfect nod to the AI involved. It just highlights how AI can find these hidden gems, things traditional methods might miss,
Right.
really accelerating the search for solutions.
So AI isn't just faster, it's finding genuinely new stuff. Okay, so if I'm a chemist and I want to use this power, what are the main types of machine learning available? The sources mentioned 3 paradigms.
Yeah, 3 main flavors in the chemist's AI toolkit. First up is supervised learning.
That's the one needing labeled data. Input, correct output.
Exactly. You showed examples. Here's molecule X, its toxicity is Y. Here's reaction A, its yield is Z. The model learns the input-output relationship so it can predict the output for new inputs.
And that breaks down into regression and classification.
Right. Regression predicts a continuous number, like a boiling point, a reaction yield percentage, maybe drug binding affinity. How strong is the binding?
Okay. And classification.
That's putting things into buckets.
Yeah.
Categories. Is this molecule toxic or non-toxic? Active or inactive? Will this reaction work or fail?
This sounds a lot like QSIR and QSPR, quantitative structure activity or property relationships, stuff chemists have done for years, but maybe on steroids now?
Definitely. Modern supervised learning has massively boosted those traditional QSAR, QSPR approaches. But the big caveat, as the sources stress, is garbage in, garbage out.
Meaning?
The model is only as good as the data you train it on. If your labeled data is noisy, biased, or incomplete, your predictions won't be reliable, like teaching a student from a flawed textbook.
Right, makes sense. Okay, that's supervised learning from labeled examples. What's next?
Unsupervised learning. This is different. You use unlabeled data. There's no correct answer provided. The goal is to find hidden structure or patterns within the data itself.
Discovering things you weren't necessarily looking for.
Exactly. A common technique is clustering, grouping similar things together.
So in chemistry.
You might cluster a large library of molecules to see if they fall into natural groups based on their structure, maybe revealing common scaffolds, or cluster reactions to find ones that might share an underlying mechanism you hadn't recognized.
Interesting. And the other one, dimensionality reduction. Sounds like simplifying things.
It is, in a way. You take data with lots of features, hundreds, maybe thousands describing a molecule, and squash it down to just a few dimensions, maybe 2 or 3, while trying to keep the most important information.
Why do that?
Often for visualization. Techniques like PCA or TSNE let you plot your complex chemical data on a 2D or 3D map.
Ah, so you can actually see the patterns.
All right, see clusters, trends, outliers. It helps you explore the data and generate hypotheses. Why did these molecules group together? Why is this one way out there? It's like that analogy of a researcher organizing a library based on the books themselves, finding connections. Great for sparking ideas.
Okay, supervised for predictions, unsupervised for discovery. What's the third one? Sounds quite different.
Reinforcement learning, or RL. This one's really exciting because it's about learning to act, to make decisions to achieve a goal.
Learning by doing. How does that apply to chemistry?
You have an agent, the AI, interacting with an environment, maybe a simulated reaction or a virtual molecule design space. The agent takes actions, like changing temperature or adding an atom. Based on the outcome, it gets a reward or penalty.
Like good job or try again.
Sort of. Through trial and error, it learns a policy, a strategy for what action to take in any given situation to maximize the total reward over time.
So it's learning how to optimize something.
Exactly. You could use it to optimize reaction conditions.
Yeah.
The AI agent fiddles with temperature, concentration, catalyst type, actions to try and maximize the reaction yield reward.
Or designing new molecules.
Yes, de novo design. The agent builds a molecule piece by piece, atom by atom, or fragment by fragment, getting rewarded if the resulting molecule has desirable properties like predicted activity and ease of synthesis and novelty.
Like those models mention, reinvent, mol air.
Those use RL for molecule generation. What's cool about RL is it bridges prediction and action. You can use predictions from other models, like a supervised model predicting activity, to guide its actions and actively explore the design or experimental space to reach a target. It's much more proactive.
That really does sound like a partner. Okay, we're talking about AI learning from molecular data, but how does the AI even see a molecule? How do you turn chemistry into numbers or text it can understand?
That's a fundamental bottleneck, actually. And how you choose to represent the molecule, that translation step, has a huge impact on the AI's performance.
What are the main ways the sources cover?
Well, one classic way is the SMILE string.
The text line, like CCO for ethanol, but more complex.
Exactly. A linear sequence of characters describing connectivity. It's compact, easy to generate, and useful for models that handle sequences like RNNs.
But downsides.
Yeah, one molecule can have multiple valid smile strings, so you need a standard canonical version, and it doesn't explicitly encode the 3D shape.
Okay. What about molecular fingerprints?
Those are vectors, basically lists of numbers, often zeros and ones. They capture the presence or absence of specific structural features or fragments.
How do they work?
Different types exist, but they essentially break the molecule down into defined pieces, paths, atom environments, predefined keys, and record which pieces are present. Think of it like a checklist of features.
And they're good for.
Very efficient for searching large databases for similar molecules. And they work well for building many standard ML models like QSIR classification. ECFPs or Morgan fingerprints are really common examples.
Got it. And molecular descriptors. Different again.
Yeah, descriptors are calculated numerical values that quantify various aspects of the molecule. Simple things like molecular weight, atom counts, or more complex things like topological indices or 3D properties like shape or surface area.
So fingerprints are more like what's there, descriptors are more how much or what property.
That's a decent way to think about it. Descriptors give you quantitative values. They're the foundation of traditional QSR/QSPR. But choosing the right set of descriptors often takes a lot of chemical knowledge.
Okay, strings, fingerprints, descriptors, and a really hot new approach.
Graph neural networks. GNNs. This treats the molecule like what it fundamentally is, a graph. Atoms are nodes, bonds are edges.
That sounds intuitive for chemistry.
It is. And GNNs are designed specifically to learn from graph data. They work by passing messages between connected atoms, aggregating information from an atom's neighborhood.
So the AI learns directly from the connections.
Exactly. It learns relevant features from the graph structure itself in an end-to-end way. You don't necessarily need to pre-calculate fingerprints or descriptors.
It's like the AI is learning the language of the graph.
That's a great analogy.
Mm.
This approach often captures more nuance, loses less information, and GNNs are getting state-of-the-art results in many areas now. Property prediction, reaction outcomes, even generating new molecules. It feels like a more natural fit for chemistry.
That shift from strings to graphs is really interesting. Okay, so we have all these powerful AI tools, better ways to represent molecules. What does this mean for the actual chemist in the lab or at the computer? Is AI taking over?
The million-dollar question. But the sources are really clear. AI is becoming an indispensable partner. It augments human skills. It doesn't replace them.
Okay, yeah, good to hear.
The role is definitely evolving, though. Chemists today, and certainly tomorrow, need to be comfortable with AI concepts, understand what it can do well, where its limits are, what kind of data it needs.
So become AI literate.
Essentially, yes. Because AI is brilliant at scale, sifting through massive data, finding patterns humans would miss, exploring vast chemical spaces way faster than we can.
But the chemist's role is still what?
Crucial. Providing the deep domain expertise, the chemical intuition, the creative spark to ask the right questions, setting the direction, designing the meaningful experiments to test AI predictions, interpreting results in context, basically providing the intellectual framework and the critical validation.
The human-in-the-loop idea.
Exactly that. AI does the heavy lifting on data processing and exploration. The chemist provides the scientific insight, steers the ship, and makes the key decisions.
So it's not AI or chemists, it's AI and chemists. A symbiosis.
Profound symbiosis, I think the sources call it. AI handles the scale and complexity. Humans handle the context, creativity, and critical thinking. It frees chemists up for higher-level tasks.
Makes sense. What's next, then? What does the near future look like, according to the sources?
Well, definitely ongoing improvements in the algorithms themselves. But a huge focus now is on AI interpretability or explainability.
Making the black box less black.
Exactly. Getting the AI to not just give an answer, but explain why it reached that conclusion. That's vital for building trust and, importantly, for generating new scientific understanding from the AI's findings.
Wow.
More integration of different data types, multimodal learning. Imagine models that learn from structure, but also from reaction conditions, spectroscopic data, text from papers, all at once.
Wow, pulling it all together.
That holds huge potential. And of course, ongoing discussion about ethics, data privacy, potential biases in algorithms, responsible use.
Yeah, important considerations. It really sounds like an incredibly dynamic time for the field.
Absolutely. This partnership, this synergy between human and artificial intelligence, it really feels like it's poised to unlock completely new ways of doing chemistry,
Yeah.
leading to discoveries we haven't even thought of yet.
Okay, so we've really journeyed through the sources you provided today. We looked at AI, ML, DL definitions, the perfect storm drivers, data, algorithms, compute.
Those landmark achievements, AlphaFold 2, Halicin,
Yeah, the different ML paradigms in the chemist's toolkit, supervised, unsupervised, reinforcement learning.
how we represent molecules, from smiles to graphs.
And ultimately, that evolving symbiotic relationship between the chemist and AI.
Yeah, we've hit the core ideas, the drivers, the impacts, all drawn from that material you shared, hopefully giving you a solid grasp of this transformation.
Definitely. So, to wrap up this deep dive, let's leave you with a final thought. We've seen AI discover totally new antibiotics, predict biological structures with incredible accuracy, fundamentally changing huge areas. If this partnership keeps getting deeper, how might it change the very process of scientific inquiry itself? What kinds of questions might we be able to ask? What kinds of discoveries might become possible that we literally can't even imagine right now?